Okay, welcome back everyone. In the last few lectures, we have learned about how full wave and how half wave and full wave rectifiers work. And in an explicit assumption that we have been making in the last few lectures is that we have been using ideal diodes. Okay, so in this lecture, we will see that what happens when we use when we design rectifiers with real diodes. Okay, as you already know that real diodes are actually non-linear devices. Okay, and it has a highly non-linear IV relationship. Okay, the IV relationship for a real diode is ID equals Is e to the power Vd by Vt minus 1. Okay, and a highly nonlinear exponential type of relationship. Okay, so since it is very hard to draw any conclusions from or design using these nonlinear characteristics, in engineering we make some assumptions. Okay, so we tend to use some models or some approximations when designing with nonlinear circuits. Okay, we use some approximations. So the approximation for real diodes that we will be using in the following lectures is that we will use the constant voltage drop model or the voltage source model of real diodes. Okay, we will be using the voltage source model, the voltage source or constant voltage drop model of the real diodes, and we will assume that the voltage drop of the diodes is about 0.1. okay, sorry not 0.1, 0.7. okay, 0.7 volt. We will try to do some analysis using this model. Okay, so first comes the half wave rectifier. What happens if we design a half wave rectifier using a real diode? Alright, so our half wave rectifier circuit was like this. Okay, and this was our input. And this was our output. Okay, so well, let's draw the graph of the input part. The graph of the input was this. Let me draw it here. I will draw one cycle. Not again. T V in, and this is our V in, and this is our V out. Okay, so if this is a real diode and if we are using the constant voltage drop model of 0.7 volt, when it was an ideal diode, whenever V in turned positive, even a little positive, okay, for even the smallest positive voltage, V in greater than 0, we had some current in our circuit. Okay, whenever the voltage turned positive, current started to flow. But we know that for a real diode of 0.7 volt to turn on, okay, so if we have an IV characteristics like this, okay, where this voltage is 0.7 volt, we know that the diode will not turn on if we apply a voltage less than 0.7 volt. Okay, so this rectifier will not start working unless the input voltage crosses the 0.7 volt threshold. Okay, so if we had an ideal diode, the graph of the output would be like this. The graph of the output would be like this for the positive cycle, and we will have no output in the negative cycle. Okay, this is the output. So, and this was the input. So as soon as the input went up, the output went up with it. Okay, no matter how small, the output is always following the input. But if we have a real diode, this is again the time. If we have a real diode, the output will not start unless the input passes the 0.7 volt threshold. Okay, unless the input crosses the 0.7 volt threshold, the output will not pass. Alright, so well, perhaps it would be better to draw it like this here. Yeah, so we'll draw it here. So unless the output passes this threshold, the input passes this threshold, the output will not go up. After the input passes this threshold, what will be the output voltage? Will the output voltage be equal to the input voltage? Suppose the input has passed the 0.7 volt threshold. Okay, input is greater than 0.7 volt. Is the output voltage equal to the input voltage? Well, no, because there will be a voltage drop across the diode now. Okay, when an ideal diode turned on, then ideal diode represented a complete short circuit. Okay, there was no voltage drop across the diode. But when a real diode turns on, if we are using this model, this voltage source model, if a real diode turns on, then there will be a voltage drop across the diode. What is the amount of voltage drop? Well, the amount of voltage drop is 0.7 volt. Alright, so then what will be the output voltage? The output voltage will be V in minus 0.7 volt. Okay, the diode will consume 0.7 volt from the input side. So what will be the output voltage? Well, the output voltage will be the input voltage minus 0.7 volt. That means that the input will go down 0.7 volt. Okay, so the input will look like this. Sorry, the output will look like this. Okay, draw this part and this part. Okay, so if the peak value of the input, was 5 volt, the peak value of the output will be, can you guess? Well, 5 minus 0.7 volt. Okay, 5 minus 0.7 equals 4.3. Okay, so well, let me maintain a table here. This is a half wave rectifier and we are using a real diode. I will also compute the correspondings for the full wave rectifier. So what is the peak value of the output? Okay, V peak. What is the peak value of the output? If the peak value of the input is Vi, then the peak value of the output is Vi minus the Vd naught, the voltage drop of the diode. Okay, all right. So the diode will consume 0.7 volt from the input side. Okay, and the negative part of the cycle will be as before. When the input turns negative, the output will be off. Okay, so as you can see from the output graph, that the output did not start as soon as the input started. Okay, as soon as the input went up, the output did not go up. The output went up after the input passed the 0.7 volt threshold. Okay, so what will happen in the full wave rectifier case? Oh, I missed one thing. You can see that in the half wave rectifier case, when did the input go to 0? Okay, the input went to 0 as when the output went to 0, okay, not before that. But if, since this is a real diode and the real diode will turn on if the input falls below 0.7 volt, so this output will turn off if the input falls below 0.7 volt. That means the output will turn off before the input goes to 0. Okay, so you can think of it like this, that I have this 0.7 volt threshold, okay, and this is the 0 threshold, 0 and 0.7. The input will turn on when, sorry, the output will turn on when the input crosses the 0.7 volt threshold, and okay, the input is rising, and when the input again falls below this threshold, the output will again turn off. Okay, so the output turns on after the input turns on, and the output turns off before the input turns off. Okay, do you get that? All right, so we will try. So what will happen if we design full wave rectifiers using real diodes? Full wave rectifiers. So let's draw our full wave rectifier. We have our diode. We have 4 diodes here and here and here. Here. Okay, then we have a voltage source in the bridge. This is our voltage source, and the rest of the circuit is as before. We have a load resistance at the output. Okay, so if this circuit is made of real diodes, what happens at a particular cycle? What happens in the positive cycle? Well, in the positive cycle, in what direction does the current flow in the positive cycle? If this terminal is more positive than this terminal, then the current comes out through here, it goes through here, it goes through here, it goes through here, and through here, and through here, here, and here. Okay, so current flows in this loop. Okay, this diode. So how many diodes are turning on in the positive cycle? Well, now there are 2 diodes that are turning on. Okay, there are 2 diodes that are turning on. So how much voltage can we see in the output? Suppose in the positive cycle, how much voltage can we see in the output? Suppose if my input voltage is like this, input voltage is like this. Suppose input voltage has a peak voltage of 5 volt. Okay, this has a peak of 5 volt. So what will be the peak voltage of the output? Okay, since 2 diodes are turning on now, not one, these 2 diodes will consume the equal of 2 diode drops from the input voltage. Okay, so these 2 diodes will consume 2 times 0.7 equals 1.4 volt. All right, so the diodes will consume 1.4 volt. So what will be the peak of the output voltage now? The peak of the output voltage will be 1.4 volt, and exactly same as the previous discussion on half wave rectifiers, a half wave rectifier turns on when the input crosses the 0.7 volt threshold. A full wave rectifier will turn on when the input voltage will cross the 1.4 volt threshold. Okay, suppose this threshold is the 1.4 volt threshold. Okay, so a full wave rectifier will turn on when the input crosses this threshold. Similarly, a full wave rectifier will turn off if the input falls below this threshold. Okay, so the output will look like this. And the same will go for the negative cycle, except the negative cycle will reverse. So let me just draw that for you. Here and here. So the negative cycle will look like this. Okay, all right, and the peak will be, previous peak was at 5 volt, the new peak will be at as we saw here, 5 minus 1.4 is for 3.6. Yeah. 3.6. Okay, so you can notice one thing, that although we can I mean, it has a short setback, that we can use both cycles here. We can use both the positive cycle and the negative cycle, but for a full wave rectifier the diode drop is more. Okay, the diode drop usually doesn't matter in power electronics applications, because we are usually rectifying a large amount of voltage. Okay, suppose we are rectifying the 220 volt AC voltage that we have in our power lines. Okay, so compared to 220 volt, your 1.4 volt or 0.7 volt is not too much. So okay, but it is one thing to notice that the diode drop in case of a full wave rectifier is more than the diode drop of a half wave rectifier. Okay, so so in general, if the peak of the input voltage is Vi and a diode drop is Vd naught, what will be the peak of the output voltage? Well, the peak of the output voltage will be Vi minus 2 Vd naught for a full wave rectifier. Okay, so let us include this data in the previous table that we have been maintaining. Vi minus 2 Vd naught. Okay, all right. Well, okay, just to maintain consistency with your notes that will be given at the end of the lectures, let me write this as Vm. Vm means the maximum value of the input. All right, so there will be less confusion if you are going through the notes. This is Vm. Okay, all right, Vm minus 2 Vd naught. Okay, so these are the waveform graphs. This is the waveform graph of a full wave rectifier with a real diode. Okay, full wave real, and this is the waveform graph of a half wave rectifier with a real diode. Okay, half wave real. These are the waveform graphs. Another type of graphs of rectifiers that we have seen are the transfer characteristics. So how does the transfer characteristics of rectifiers change if we use real diodes? Okay, so let's have a look at the transfer characteristics. Transfer characteristics with real diodes. Okay, let's just draw the transfer for the ideal diodes once again. So the transfer for the ideal diodes was, let me draw the half wave one first. The half wave one was like this. Okay, what does this mean? What this means that this is the V out and this is the V in. This means that as soon as the V in goes up, as soon as V in increases, V out increases with it. But if we are using real diodes, we know that V out cannot turn on at as soon as V in goes positive. Okay, V out will turn on only if V in passes the 0.7 volt threshold. Suppose this is our 0.7 volt threshold. Okay, this is our 0.7 volt threshold, and this is a half wave rectifier. So if we are using real diodes, what will be the case? Well, our graph will go up once the 0.7 volt threshold has been passed. Okay, if this is our 0.7 volt threshold, then our graph will be like this, and the negative part will be like as before. Okay, the slope will also not change. Okay, how does this graph come? Well, we saw that what is the relation of the output with the input. The relation of the output with the input was, for a half wave rectifier, V out equals V in minus 0.7. Okay, so what type of graph is this? This is a graph of y equal to x minus c, with c equals 0.7. So this graph crosses the x-axis at the point c. So since this is 0.7 and m equals 1 here, so the slope is also 1. This is the transfer characteristics of a half wave rectifier with a real diode. What will be the case for a full wave rectifier? Okay, let's draw the full wave rectifier's transfer characteristics once again. The full wave rectifier's transfer characteristics was like this, this part and this part. Okay, both had this had a slope of 1 and this had a slope of minus 1. Okay, so the same logic as we gave in the half wave case, that the input cannot go up as soon as the output goes up, because for real diodes we have to cross a threshold. What is the threshold for the full wave rectifier? Well, the threshold is 1.4 volts this time, not 0.7. Okay, we have to cross a larger threshold because we had two diodes. Okay, we needed two diodes to turn on for a full wave rectifier. So the output will go up once only when the input crosses the 1.4 volt threshold this time. All right, 1.4 volt. So okay, so what will be the graph of the positive part? Well, if this is the 1.4 volt part, 1.4 volt threshold, our graph will be like this. Okay, similarly for the negative part, now the negative part also has to cross the threshold of minus 1.4. Okay, so this will be, if I have minus 1.4 here, then the graph will be like this. Okay, all right. As before, the slope of this part is 1, the slope of this part is minus 1, and between these two regions the rectifier will not produce any voltage. Okay, from minus 1.4 to plus 1.4 there will be no voltage at the output of the rectifier, because no diode will turn off. Neither the negative cycle diode will turn off, nor the positive cycle diode will turn off. Okay, so these were the characteristics of the rectifiers. If we design them using real diodes, we will actually find the value of another metric that we can use to see how well our rectifiers are performing. Okay, so see you in the next lecture.